So this week we have Ryan Murray speaking. So Ryan did his PhD at CMU, and then you did your postdoc at Penn State, if I remember correctly, and now he's the assistant professor at North Carolina State University. He's going to be talking to us today about consistency of Cheeger cuts, total variation, isoperimetry, and clustering. So thank you, Ryan.
Excellent. Thanks a lot, Matthew, for the introduction, and thanks to the whole committee for the invitation to speak. I'm glad to be speaking today. Just kind of by way of logistics, if you have questions as we're going, you can write them in the chat, and we have both Matthew and Nicolás who helps with this work, who can probably address some of the questions, who can address questions, or also if you'd like to, if you prefer to unmute yourself and ask, or Matthew can unmute himself and ask, these are all options. I want to make sure people are understanding as we're going through the talk. So just like Matthew said, I'm going to be talking about consistency of Cheeger cuts, kind of with these ideas related to total variation, or I'm mostly going to be focusing on perimeter, isoperimetry, which that's a word that that I'll kind of say a lot more about later, and clustering, which is really our machine learning or data science problem that we're going to be considering. All right, okay. So to kind of start out, I want to introduce the data clustering problem. So let's suppose that we're given some number of data points. I'm always going to think of n as the number of data points. And our goal is, given just those data points, we would like to break them into meaningful classes or pieces. So kind of one of the very most classical examples of this might be the MNIST data set. So here I've taken this picture from Wikipedia that shows a bunch of kind of representative data points within the MNIST data set. And these data points are all images. So each one of these xi's is an image. And you can see here, we as humans, or you know, people that know numbers, we look at these and we say, oh, of course, these are just different numbers. And even though they're shaped slightly differently, or you know, people draw them in slightly different ways, we can identify them into meaningful pieces. That these are zeros, these are ones, and these are twos. And we don't need labels to do it. We can just look at the shapes and kind of infer that. So we can see this difference, and even somebody who used a different number system could probably still identify some patterns here. But what we'd like is some algorithm that can figure out these patterns, can identify these kind of meaningful groups without labels. Now here, even for this relatively simple kind of machine learning example, you're still looking at data points that are in r to the 28 squared. So I'm pretty sure these digits are 28 by 28. And that's still a pretty big number. You're still talking about r in the 100s, or in the hundreds. So this is still a challenging problem in the sense of we're embedding this in a relatively high dimensional space in some sense. Okay. So why should we study clustering? Well, clustering is kind of the most basic unsupervised learning problem that's out there. And in many cases, in machine learning or data science applications, we might not have labels for all of our data. It just might not be available. It might be expensive or difficult to acquire labels for a lot of the data. Similarly, clustering oftentimes gets used when we're doing visualization or exploration, trying to understand what's going on. In some sense, we're trying to understand the geometry that's underlying the data, and I'll say more about that later. And it's oftentimes a first important step in some machine learning application, okay? So this isn't, I'm not using neural networks to do some type of classification or fitting problem. We're really looking at kind of a very basic first problem in clustering is the thing that we're thinking about here. Having said that, there are many different ways, many different algorithms that have been proposed for doing clustering. And there's tons and tons of formulations. I can't talk about them all. I'm choosing to talk about a specific one. Actually, one time I gave a course to some people in industry, and I had them, let's go ahead and give every person in a course one version of clustering. And I think we had 15 different projects where they studied. So there are, dozens of these different types of algorithms. They all have slightly different flavors and different advantages and disadvantages. But just to say kind of a few high-level ideas, there's many ways you can pose this clustering problem. One option is to do something that's parametric. And this is the approach that oftentimes kind of gets used in a first statistics course or something. We say, well, let's go ahead and think about some representative points, k representative points, and try to find k-representative points that partition the data in a way that kind of minimizes some error. But you've parameterized it by k points in RD. One could also use something like expectation maximization. This is, again, a parametric algorithm for describing clusters. Kind of on a more abstract level, there are questions about what does it mean to have found a cluster. So are we thinking about areas of high density? Are we thinking about how connected different kind of data points are? Should we represent clusters by their boundaries or by kind of the volume that they contain? Should we think about representative points in the center or not? These are all kind of very abstract questions that you have to address when you're picking a particular formulation of the clustering problem. I do want to mention that this is oftentimes kind of related or paired with some type of dimension reduction. So oftentimes you want to kind of reduce how complicated your problem is, and you want to take something in very high dimensional space and reduce it to something that's simpler to do inference on. And something like k-means or dimension reduction, like these things all are closely related to one another and get used to simplify problems and improve performance of inference and learning algorithms oftentimes. Traditionally in the computer science literature, many paradigms for clustering are connected with graph partitioning. And this is actually the kind of paradigm that I'm going to be talking about during this talk today. And finally, I will mention that there are many different relaxed versions of some of these algorithms. And in particular, one is spectral clustering, which we heard about in this seminar just a few weeks ago when Franca gave her talk. So these are all different kind of things going on or different paradigms one might consider very generally when we're thinking about the clustering problem. But having kind of given this introduction to the problem of clustering, now let's turn to exactly what the concrete goal of this talk is, what I'm going to talk about. So the goal in this talk is I want to talk about one particular clustering method, which is based upon Cheeger cuts, which is sort of a very simple, at least conceptually, method for constructing partitions of a graph. I'm going to, as we go along, a big message of this talk is going to be when you're doing problems, optimization or variational problems on graphs that are based on sampling in Rn, there's an underlying continuum structure that gives you leverage and understanding and studying and providing guarantees for these algorithms. And so a big part of this talk will be related to the continuum theory that's underlying some of these methods. And then at the punchline of the talk is I'm going to describe some new results that provide some concretely quantifiable consistency guarantees for the Cheeger cut problem towards its asymptotic limit. So kind of in the vernacular of statistics, we would say that these are quantified asymptotic consistency results. And one kind of other higher level message that I want to give is that the limiting continuum theory, which is actually relatively well behaved and is connected with the isoperimetric problem, actually sort of alludes to the fact that the Cheeger cut problem in this setting is perhaps nicer than the very general Cheeger cut problem on graphs, okay? And this is something that I'm not going to attempt to make concrete yet, and in fact, we haven't made this completely concrete yet, but I hope that the analogy should make it clear that there is something underlying this problem that is rather well behaved, and that we can use both to understand it and hopefully in the long run to provide a kind of better theory for Cheeger cuts when we try to solve them directly on the graph level. Okay? So let's go ahead, and I want to now kind of give a very basic description of the Cheeger cut problem. And we're going to kind of do this by dialing all the way back and thinking about kind of abstractly what is clustering. So we're thinking about data points that are embedded in RD. All of the pictures that I have here will be R2, of course. And I want to identify coherent groups in my data. So here I have this cloud of data points, and we want to identify coherent groups. Now, what we're going to assume throughout this talk is that the data points that we're observing are in fact sampled from some underlying distribution in RD, okay? So I'm assuming that I have some nice underlying distribution mu that is supported on a domain omega, and that the data points that I've observed are in fact sampled from that underlying distribution. Now, this is definitely a modeling assumption, and it will not hold in every situation you can think of, but it doesn't seem unreasonable that something like this should hold in at least many settings. Okay. Now, if we forget about the data points for just a minute and kind of say, well, how would you pose the clustering problem for a continuum domain? We can ask this question: how would I construct a partition of this continuum domain? So if I went to, for example, my 8-year-old, and I said, could you please split this into 2 pieces? How would she do it? Well, I can almost guarantee that she would draw this line here, or something very close to it. That she would draw this line straight up and down that cuts it into 2 pieces of roughly equal size, and that straight line is kind of the shortest one possible. And she would view that as the most natural way to construct a partition of this continuum domain. Now, she could have drawn a line horizontally from left to right, or she could have drawn a very curvy line that is very irregular. But I think that most of us intuitively, when we think about splitting these domains into multiple pieces, the way that we think about it is we want to do 2 things. We want simple, shorter boundaries. So we don't draw a squiggly line, we draw a straight line or something very similar to it, maybe a smooth curve. And we want the size of the partitions to be similar. So in this particular case here, the piece on the left and the piece on the right are exactly the same size. Okay. So if we think about this from the framework of the calculus of variations, how would we encode those 2 goals as an objective function? This is kind of what one would try to do classically if we pose this as a continuum variational problem. So we have kind of, okay, so in this last slide I said we want shorter boundaries and we also want to have partitions of similar size. So when we talk about short boundaries, what do we mean? Well, it means that we're going to measure the perimeter of this boundary and we want to make that as small as possible, okay? Now here I'm going to kind of abuse some notation throughout and I'm going to write the perimeter of this set A sub omega. And what I mean by that is just the surface area of the boundary of A inside the domain omega, okay? So when I look at this partition that I've drawn here, I'm only charging for the dotted line down the middle and not for the solid line on the outside of the domain, all right? And when I say that I want the partitions to have comparable size, there's various ways that I could implement this in a cost functional. So the first example that I write here is what's called the Cheeger energy, and it simply takes the perimeter of A and it divides it by the minimum of the volume of A and the volume of A complement, okay? Now I've written this in kind of a very, very simplistic form, forgetting about the measure mu, but with the measure mu, all you do is you replace those vertical bars with mu of A and mu of A complement, okay? All right, there's other options for ways you can implement this kind of, this goal to have partition sizes be comparable. So one option is instead of using a min, you just multiply the size of A by the size of A complement, and that's called balanced, these are balanced partitioning problems. And then there's a third option that's called modularity clustering in some settings, or it's related to modularity clustering, where what I instead do is I add the size of A squared plus the size of A complement squared multiplied by some constant gamma that I would have to pick, okay? So all of these functionals are going to encode those 2 goals. The goal to make the area of the boundary of A as small as possible and to keep the size of A and A complement comparable. They don't have to be exactly equal, but they should be of comparable size. All right, so this is our continuum Cheeger cut problem, or our Cheeger set problem would be to minimize over over sets A, this perimeter divided by the minimum of mu of A and mu of A complement. And a first question that someone would ask if they were approaching this from a variational standpoint is they would say, do minimizers exist to this problem and are they well behaved? And the answer to that is yes, and it's deeply related with what's called the isoperimetric problem, okay? So let's just for a moment forget about this denominator that penalizes the size of the different partitions, And let's go ahead and just think for a second about minimizing the perimeter subject to some constraints. So here I've written it in kind of a vague way intentionally, so it could mean different things depending on the setting we're thinking about. But here I'm saying I'm minimizing A over some set of class of sets Q. And I'm minimizing the perimeter of A subject to A being in some class of sets Q. And perhaps this class of sets might be sets that have a specified size. So I might fix the volume of a set and then ask, what's the smallest perimeter that includes, that has a fixed volume, okay? So if we consider this problem of minimizing perimeter subject to, for example, a volume constraint, this is maybe the most studied problem in the calculus of variations. If not the most, it's very close to it. It actually dates back to thousands of years ago, to the Greeks. They have mythology about this. It's deeply connected with problems from geometry. So there are things called minimal surfaces. There are things called constant mean curvature surfaces that are exactly the necessary conditions for this variational problem. And it turns out, kind of, if I write down the necessary conditions, I get, in fact, an equation that involves the curvature of the boundary, okay? So this, if you've seen this before, this is kind of easy. And if you haven't seen this before, it's actually kind of hard to parse the first time. But basically, this equation down here at the bottom, the sum of kappas is equal to C, says that the curvatures of my surface, they sum to the same constant no matter where I measure on the surface. And these curvatures, okay, you have to define them as some derivative of the normal vector, and they're the eigenvalues of that. But you should really just think about them as kind of the principal curvatures that you would have studied in like a calculus in 3D class. Okay. Now, this constant mean curvature equation, this sum of kappas is equal to C, actually really has some underlying kind of elliptic form. Okay, so it's really this first bullet here, this may be written in a form like Laplace U equals C. This should really be in quotes, like that's not a precise statement, but there are many analogies between the two and you can connect them in a very similar way. And just like elliptic equations, this equation Laplace U equals a constant or a smooth function, the solutions to this constant mean curvature equation, in fact, have to be very smooth. At any point where they're for one-time differentiable, they actually have to be infinitely differentiable. And you can show that the set where they're not C1 is very, very small, and in low dimensions, it can't even happen. So some simple examples of constant mean curvature surfaces that one might kind of be able to visualize are things like pieces of circles or spheres. Or you can come up with more complicated surfaces like this, this catenoid on the right. Again, these pictures are from Wikipedia. But all of these surfaces that you get when you look at constant mean curvature surfaces are indeed exceedingly smooth. They're very nice in some sense. Okay? All right. So now we can return here to this continuum Cheeger set problem, where we're minimizing over A, this perimeter divided by the minimum of these two areas. And one can show using kind of very classical tools from the calculus of variations that minimizers exist, just using basically the isoperimetric inequality and some compactness of the perimeter with respect to L1. That in some generalized sense, the boundaries have constant mean curvature, and modulo some very, very small set, they have to be analytic surfaces, okay? So even if the picture is slightly more complicated than this domain in R2, where I drew this dotted line that was straight, it turns out that, that when I minimize this kind of continuum variational problem, I get something back that is very, very well behaved, which is what we would hope. So now we can ask the question, how would you modify this to work, or what's kind of the analog when we're thinking about this data cloud, this finite set of data points? Well, one thing that we can notice kind of immediately is if we're thinking about mu of A and mu of A complement, this actually is not so hard to come up with a good analog in the setting of these finite points. So if I look at a subset of this data cloud, I can kind of measure mu of that subset by just counting how many points are in it, and looking at kind of the relative number of points that are in the subset I'm looking at. So we just use cardinality to define this mu of A and mu of A complement, and we're kind of okay in terms of the bottom part. Okay, so Stefan asked, are there regularity conditions for mu to get constant mean curvature surfaces as minimizers? So I have swept under the rug here anything about mu in the discussion at the start to keep things kind of concrete. But later on we can deal with mu and we still get regularity, but you do assume that mu is sufficiently regular to make sense of the equations that you have. So that's a good point. You do need to assume something about mu if you want to have similar regularity, but we can think about that more later. At the moment, it's still kind of, we're just trying to understand the problem. All right, so then here, if we're thinking about the analog of the perimeter for finite data, we kind of need to impose some type of additional structure. So kind of looking at the data points, if I just look at a particular subset of these data points, understanding what the perimeter between that subset and its complement is doesn't really make sense unless I impose some additional structure. And the structure that we chose to use, and that many others have indeed chosen to use in this context, is what's called a random geometric graph. Okay? So we're going to take these points, these random points that are sampled from this distribution mu, and we're going to treat them as a weighted graph. So we're going to think of each data point as a vertex in our graph, and then we're going to have the weight between two different vertices in our graph be given by some kernel of the distance between the points. So here, this wij is the weight between vertex I and vertex j. This eta is some decreasing kernel. If you'd like to just think of it as the indicator function 0, 1, that's fine. Or you could think about it as something smooth, like a multiplier or something. But it's mapping it's mapping the positive real numbers to the positive real numbers, and it's decreasing. And then here, the argument is xi minus xj, the distance between xi minus xj, so that's how far apart they are, divided by epsilon. Okay, so this epsilon is a parameter that we're allowed to vary, which say at what distance we're thinking about points as being related. Okay, and the point here is that the weight decreases as my points get further apart, and that points within distance epsilon, roughly speaking, are considered related, whereas points that are much further than epsilon are not considered related. Okay. So down here at the bottom, I've drawn this this graph structure that maybe one would get using these weights for kind of a small piece of the data cloud that I've been using. So maybe up here I have this data cloud, and then if you kind of zoom in on that part in the very center, you get this little piece of the graph right there. And then I've drawn using these blue lines kind of the connections between the points. So I would suppose I'm using this as 0 or this indicator function kernel, and so the points that are considered related to each other, I've drawn a blue line between them, and they would have weight 1. Okay. All right, so these random geometric graphs actually have been very well studied in a variety of settings. So one thing to say is that there are many variants of these random geometric graphs that are perform better in different settings for different reasons. So there are things called self-tuning graphs that are able to handle boundaries in the data. There are things called KNN graphs that are oftentimes what's actually implemented in practice that don't use a bandwidth epsilon, but instead look for the k closest points. These types of graphs have received a lot of attention kind of under maybe the name manifold learning. And in particular, they've been used to understand the geometry kind of underlying data by means of studying the graph Laplacian and the spectrum of the graph Laplacian and the eigenvectors of the graph Laplacian, and then trying to use that to kind of find some way of representing the underlying geometry of omega, essentially. And this connects to all sorts of different works. So there's this work from the 1960s that I like to kind of reference. It's this old paper called Hearing the Shape of a Drum, which basically asks, given that we have the eigenvectors or the eigenfunctions of a manifold for the Laplacian, can we infer something about the geometry of the manifold? The answer is you can't infer everything, but it does give you a lot of information. And then there are these other kind of works more related to machine learning, relating to diffusion maps, manifold learning. There's Laplacian-based supervised learning. These are by people like Koifman and Belkin and Niyogi in kind of the 2005 range. And there was this rigorous connection that has been drawn between graph Laplacians on these random geometric graphs and continuum Laplacians that has been kind of studied over the last 15 years. And I put just a few names here. I'm not intending to be exhaustive, but just to kind of give some indicator that this is something that people have considered quite a bit. And so, okay, so I'm not going to say much about these graph Laplacians, but I just am trying to say that, that they have been considered in a lot of depth and are something that people are very interested in. So these random geometric graphs are useful in other contexts as well. All right, so once we've defined this random geometric graph and these weights between the nodes, then one defines what's called a cut functional, okay? Which basically just says, let's go ahead and penalize, if I specify a subset A of my graph, then the cut energy of that set A is given by the number of edges I have to cut between A and A complement. So if I kind of think of A and A complement and I'm cutting between them, what's the total weight that connects the two, A and its complement, essentially, okay? And this is something that you can kind of implement, you can at least measure it directly given a subset of our graph. And then the Cheeger cut problem, which has kind of been very widely studied in the computer science community especially, has to do with minimizing the cut energy, which is this cut over this graph. And I've written it sub epsilon and n to remind us that our graph does depend on epsilon and n, divided by the minimum of the relative sizes of A and A complement. And here this mu n is just this empirical measure, this cardinality basically of the set A and the set of A, the set A complement. Okay, so in this little click that I drew, this little piece of the graph, if I were to say what is the Cheeger set, the Cheeger cut of this graph, what I would do is, okay, I drew the blue lines, those were the links between the different vertices. And my guess here is that the Cheeger cut probably would be corresponding to this red line. I would cut those edges, and then the two components, this kind of bottom right subgraph and this top left subgraph, that would be A and A complement, and that would be your Cheeger set, or your Cheeger cut, sorry, in the context of this very small graph that I've drawn here. Okay. And then if we thought about, all right, let's go ahead and do the Cheeger cut problem for that entire big data cloud, I think it would probably end up looking something like this, with the red dots being in A and the white dots being in A complement, and the cost of that cut being exactly the cost of cutting those links between these kind of in the last slide, in this little diagram, okay? All right, so, let's say just a few things briefly about this Cheeger cut problem. So kind of the bad news first. So the bad news is that the general Cheeger cut problem, if you want to find an exact solution, it is NP hard. And the reason for this is that it's really a special case of this graph partitioning problem. And when you're doing these graph partitioning problems, at least I don't specialize in these kind of discrete optimization problems or these kind of NP hardness type results. But my understanding is that there's no way to really be sure that your solution is the best one unless you check, most of the possible subsets. In some sense, you have to do some type of combinatorial search over subsets that ends up being kind of scaling poorly in dimension. Okay. But regardless of whether we want to think about it as an NP difficult problem, it still is this kind of difficult non-convex optimization problem. that doesn't go away whether or not we're thinking about NP hardness. It still is a non-convex optimization problem that is quite challenging. In particular, because we're requiring these A are sets, and so it's we haven't relaxed it at all. So it's a challenging non-convex optimization problem. So there are various approaches that people have tried to use to relax this problem or make it more friendly. So one observation that one can make is that cut energy, we could rewrite it because everything is 0, 1 valued as the square of the difference between indicator functions. Okay. I might have written something wrong here. I have to think about this. Maybe there should be an A complement. But either way, you can write it in a form that looks like this. And if you relax the requirement that I look at indicator functions and instead permit one to take arbitrary function values in R, then this actually turns out to be exactly the spectral clustering problem. So this was first proposed by some people in machine learning and computer science in the early 2000s. Good important properties about its consistency and its relation to the Cheeger cut problem were studied by von Luxburg and many others in the early 2000s. And indeed, there was a talk just this last week by Nicolás and Franca and Bamdad that addressed this problem kind of in a similar framework to what I'm talking about today. You can think about spectral clustering really as an eigenvalue problem, as an eigenvector problem. And so by relaxing the formulation, you can reduce it to an eigenvalue type problem. There's also an alternative approach for approximating the solution to this cut problem, or this Cheeger cut problem. One option is to try to embed your graph, which has n vertices, into Rn, and then do some type of approximation algorithm. So this is something that computer scientists worked on something like 10 years ago. The problem is that as n gets large, this is problematic. So this isn't thinking about an embedding into RD, kind of the ambient space that we're living in. We're thinking about this graph as an object with n vertices, and the embedding that they use embeds it into Rn. So this is also kind of challenging as n gets large, and it isn't leveraging the underlying structure. And one of the kind of takeaways that or kind of the points I want to make here is that these approaches involving relaxation, involving these graph approximation algorithms, they're posed for general graphs, and they ignore any continuum structure. And I think that the continuum structure often gives you a lot of leverage for studying these problems. So a question that we can ask, and indeed many people have asked this, or we're still asking this, is what's the best way to compare these discrete and these continuum minimizers if we're thinking of the discrete objects as kind of samples or approximations of the continuum one, okay? And so if we look at these two pictures of this Cheeger cut, in this case here for the graph, and this Cheeger set in the continuum, they're already starting to kind of look like each other. And the question is, can we kind of understand them kind of in some unified framework, or can we connect one to the other in a rigorous and hopefully easy to understand way? But what are the challenges to this idea? Okay, so we have this discrete problem and we have this limiting continuum problem, and we'd like to say that the two are related in some concrete way. But why is this hard? Well, this is a non-convex random variational problem that optimizes over all subsets either of a graph or of RD. And there's some connection with NP hardness that we'd hopefully think isn't as bad as we'd like, but it could be really bad. So maybe it's really hard to compare these continuum and these discrete objects. There's definitely some obstacles to trying to understand this. It's not trivial. It's challenging. So one thing that I will say is there is a classical approach from kind of learning theory related to like VC theory, where one tries to describe kind of an asymptotic consistency. So if we think about these discrete to continuum objects, it's some type of asymptotic consistency. And a classical approach from kind of the computer science, machine learning viewpoint would be to understand the capacity of your set of functions that you're using, and then use that to infer some type of limiting asymptotic behavior or asymptotic consistency. Okay, so I've written this in kind of a funny way, which would kind of maybe be more familiar to people who do VC theory. But basically we're saying, look, if I compare some empirical energy E sub n with some limiting energy E epsilon or some kind of mean energy E epsilon, and then I can look at the supremum over functions in some function class f, then as long as that function class f isn't too expressive, then in some limit I can control the difference between these two quantities. Okay, this is very vague and is kind of just intended to give some intuition, but basically the takeaway is that if we can restrict the class of functions that we're considering when we're doing these variational problems, oftentimes you can prove asymptotic consistency in kind of a straightforward way using just probabilistic techniques. So if here we write down this kind of cut energy or this Cheeger energy on the graph in kind of this rescaled way with appropriate n's and epsilons in the denominator, and then we take kind of an expected value and we get this E sub epsilon on the right, which is some type of non-local perimeter. If we restrict to a class of very nice sets, in particular sets that have bounded curvature, then it turns out that we can show some type of good convergence properties. Okay, so this work was done by Arias Castro and some other collaborators around 2012. And it relies on basically some detailed concentration estimates, some U statistics type results to prove that this type of thing works. But they readily admit in their work that there is no reason a priori that you can justify restricting the class of nice sets in this graph setting. So if I consider the minimizer of this Cheeger cut problem, it's not a priori clear at all that the minimizer should look like something with bounded curvature. And indeed, this cut energy can't see very well oscillations that happen on length scales epsilon. And so one can ask the question, well, is there a way or a path through the analysis that permits you to find to prove asymptotic consistency regardless of whether we know a priori that we have nice regularity? And this is something for the discrete problems. And kind of Nicolás has a kind of saying that he says for this, he says, we need to pass the probabilistic estimates where they do no harm. So in this setting, in the setting of kind of this VC theory, these concentration estimates just kind of done in the most classical way, you run into this problem that you need underlying regularity of these discrete minimizers, and we can't do that. We've kind of required the concentration estimates to happen with these sets that we don't know are regular. So instead, we need a different approach. Okay, so one of the big steps towards the work that we did was to prove just even an asymptotic consistency result for these Cheeger cuts on graphs, even just that they converge at all. And there are a series of works kind of around 2016 with Nicolás and some of his other collaborators that established exactly an asymptotic consistency result. And it reads something like this. And I've suppressed things like logs of n. I've suppressed kind of technical details. But this is just to give the idea that if we specify a specific kind of decay rate in epsilon, so if I say that epsilon is going to 0, but not faster than n to the minus 1 over d, essentially, modulo some log terms, then we can show that the Cheeger constant, so the Cn here is the minimizer of the Cheeger cut energy when appropriately scaled. And this C here is the minimum of the Cheeger set energy in the continuum. And what we can say here is that these Cn's converge to a modulo a scalar that depends on eta version of the Cheeger set energy. And in addition, we have that the AN stars converge to an A star. So A star here is the limiting Cheeger set, the continuum Cheeger set. And AN star are the underlying Cheeger cuts on these data clouds. Okay? And one can say that the AN stars have to converge to A star in some type of L1 topology. Okay, that's very, very vague and there's lots of technical details. How do I actually compare sets on graphs with sets in the continuum? But at least from a high level, this describes the type of consistency that one gets. And the ideas for all of this come from the calculus of variations. So it uses tools called gamma convergence. It basically looks at these non-local TV or perimeter energies and compares them to local TV or perimeter energies. And then there's these estimates on transportation distances that were very important in these works at that stage. But one thing that I'll remark is that there are no rates in any of these works. There's nothing quantified about how the Cheeger constants converge, nor about how the Cheeger sets converge. And things like these rates provide performance guarantees and robustness guarantees for these algorithms. And I think is really a place where mathematicians can offer something, is in saying concretely how well one can expect these algorithms to perform, especially with respect to the number of data points that you have. Even so, leaving aside the issue of rates, if we think about abstractly what this represents, this is pretty cool. So what does this give us? This gives us a choice for parameters. So we know how we have kind of a set of parameter ranges for epsilon for which this works. Epsilon should be bigger than n to the -1/d, but it should still go to 0. I call this the Goldilocks regime. So there's a fairy tale that gets told about Goldilocks, who didn't like the porridge too hot or too cold, but just right. And here this epsilon tells us what just right is. And even so, in addition, we're talking about the convergence of minimizers for these non-convex random variational problems, and we're taking both epsilon to 0 and n to infinity simultaneously. So we've said quite a lot about what's going on with this Cheeger problem, which a priori sounds pretty scary. It's this non-convex random variational problem. Okay, so at this stage now, I'm going to talk about what Nicolás and Matthew and I worked on kind of over the last year relating to this problem. And I want to start out by just stating the results. Again, I'm suppressing some technical details. I'll mention a few of them later, or some technical assumptions. I'll mention some of them later. But just to give you kind of an idea of exactly what's going on here. So assuming the exact same Goldilocks regime, this epsilon is is going to 0, but not faster than n to the -1/d. Then with kind of very high probability, one can show the difference between the Cheeger, the minimizing Cheeger energy, so this Cheeger cut number, C epsilon n, minus this rescaled Cheeger set energy, sigma eta sub c, that this is bounded by, okay, and then I have this n to the -1/d over epsilon plus the square root of epsilon, okay? So over here on the right-hand side, what in the last slide was just a consistency result saying that the two converged to each other, or that the CNs converged to this sigma sub eta. Now we've kind of upgraded this and said, look, we can actually provide a bound on how large that difference can be, and we can show how that bound goes to 0 as epsilon goes to 0 and n goes to infinity. Okay. So this gives a concrete rate of convergence for Cheeger constants. So I want to just mention briefly, maybe in like 2 minutes, some of the ideas in the proof. And kind of the message that one can get here, kind of from a high level, is that one needs to be careful where they do the probabilistic estimates and with what objects. Because if you try to do the probabilistic estimates with the wrong objects, you'll get stuck. And you'll end up needing things like the regularity of the Cheeger cuts, okay? So the first thing one needs to prove is an upper bound. So here, what one essentially does is one replaces the perimeter of kind of the minimizing Cheeger set in the continuum with some non-local perimeter sub epsilon. So this was the non-local approximation that involved eta, but still in the continuum. And then one adds and subtracts this rescaled cut energy, okay? I may be suppressing some constants here, but I think that the idea is pretty clear. The first term on the right-hand side of this inequality here, you just say, well, because the AN okay, there should be a star there. Because the minimizing Cheeger cuts, because they're minimizers, we can bound the first term on the right there by the discrete minimizer. the discrete minimizing energy. And then the second term on the right-hand side here, this perimeter sub epsilon of A star minus this rescaled cut energy of A star, we can actually bound just using concentration inequalities. And the key here is that this set A star is fixed. And so you just use classical concentration inequalities, you use these U statistics, and you can get a good bound on this, this term, this difference between the perimeter sub epsilon and this cut energy, okay? On the other hand, one needs to also get a lower bound. And this is, I would kind of say, is the more difficult or challenging part of this analysis. And really what one does here is one says, let's suppose that we're given any set on the graph, A sub n. And then given that set A sub n, we need to construct some set A in the continuum, which has comparable mass. So this mu n a n minus, or comma a is the distance between the two. I should have written that different, sorry. But we can kind of bound the difference between the two sets, the continuum approximation A and the graph subset AN. And we can also bound the perimeter of this set A with this cut energy. And this doesn't require any structure on the special structure on the sets A sub n. What it really does is we're just taking some type of convolution. We're convolving it with some nice kernel, and then we're able to carry through the estimates in a careful way. Now, there's a lot of technical details that get suppressed here. You have to use these monotonicity and convolution results for non-local TV energies. These things aren't easy to show, but the idea basically here is that we prove these kind of interpolation results for arbitrary sets, and they don't require any sort of arbitrary or any sort of a priori regularity. They don't require things like bounds on curvature. All that they require is that we know something about the cut energy. And for minimizers of these Cheeger problems, we know a lot about the cut energy. We actually know what the cut energy converges towards, so we can say a lot about this, okay? And at the end of the day, what this will give us, kind of this idea here, allows us to write some type of upper bound on the Cheeger set energy by the Cheeger cut energy plus some error term, okay? And you put all these things together and you get some concrete rate of convergence for the Cheeger constants. All right, so once we've proven that the Cheeger constants converge, a very natural question is, can you say something about the sets? It's nice that the energies converge to something, but do the underlying sets actually converge to something? Or can we quantify how they converge? We've quantified the convergence of the energies. Can we also quantify the convergence of the underlying sets? And this kind of is most precisely motivated by just a simple example in calculus. So if we think about the convergence of minima towards, given that we know convergence of values, can we also imply convergence of kind of the minimizers, the x's? So this example here might illustrate this better than I can say it. So let's think about the function f of x is equal to x squared. The minimizer is at x star equals 0. Then if we can put some upper bound on the function value at a point x, so if we can say that f of x minus f of x star is smaller than delta, then what one can actually say is that the distance between x and x star squared is bounded by some constant times delta. And this basically just says, look, the energy is locally convex around its minimum. And so then we can quantify the distance between x and x star just using the difference between the energies of x and x star. Okay. So this is a very simple calculus idea that you can just kind of write down explicitly. It turns out that an analogous idea holds for the perimeter function, okay? So I'm stating this here as a meta theorem. Suppose that E star is a smooth, isolated, local minimizer of an isoperimetric problem. Again, this is all in quotes. An isoperimetric problem, you have to specify, do I want something that's constrained or not? What does it mean? Then it turns out that that we have a stability inequality that looks like the form down here below. So the L1 difference, the set difference between E star and E squared, is going to be smaller than some constant times the difference between their perimeters, okay? Now, I've stated this here as a meta theorem because you have to specify your setting. I'm not saying this holds for every isoperimetric problem that someone can imagine, but there are several different variants of the isoperimetric problem, for example, a mass-constrained isoperimetric problem, on like a manifold, for example, a compact manifold. for which something like this is known to hold. And the way that one should interpret this is that the isoperimetric problem is locally convex in some appropriate sense. So we can think of it like that quadratic. Okay, we can quantify how it's locally convex kind of in an L1 type topology, if you want to think about it that way. Kind of just to illustrate here, if we think about fixing a volume, then we have the circle is the minimizer of the isoperimetric problem fixed to that volume in R2 here, for example. And then I look at some polygon here, and I say, look, the perimeter of the polygon is relatively close to the perimeter of the circle, and it encloses the same volume. Then I can actually show that the polygon in an L1 sense is also close to the circle, okay? So that's just an illustration of the type of setup you would have. There, E star would be the circle, and E would be the polygon, and you would be able to quantify the L1 distance between the two by using the perimeter, using an inequality of the form above. So this has been intensely studied by many people, especially in the Italian school. There are noteworthy works by Fuscomaggi and Fratelli and Cicalesi and Leonardi. And more recently, there are these works by Chodas, Engelstein, and Spoilor that establish these types of results in various different settings for different isoperimetric type problems. Okay. It turns out, so kind of the punchline here, the end of the story for our paper was that exactly using these isoperimetric stability results and kind of shoehorning them into our problem, we could actually prove an analogous stability result for the convergence of the Cheeger sets, or the Cheeger cuts towards the Cheeger sets. So here I've kind of written this chain of inequalities. What we're able to say is that the L1 difference between the Cheeger sets on the graph, which are the AN stars, and the limiting Cheeger set A star, is indeed bounded by, okay, I have here the difference between the constants, so that's the difference in the energies. And then I'm raising it to some kind of funny power, d minus 1 over 4d. Think of it as 1/4. It's probably easier to think about it that way. It's roughly 1/4, which if we wanted to, we can just quantify using kind of the previous estimate we had on the Cheeger constants to give something like n to the minus c over d for specific choices of epsilon. Okay, so what does this do? This gives us a quantified, or let's see here. Okay, then maybe I'll say a couple of caveats here. So the first thing I said, under mild assumptions on the Cheeger sets, this is some assumptions about the limiting variational problem. So we state it for compact manifolds with some specific assumptions, but they're relatively mild. Also here, I've kind of suppressed the fact that we can't directly compare AN star and A star. We have to use some type of extrapolation map, but this isn't so bad either. And then finally, I will readily admit something that a computer scientist would immediately ask is, are these exponents optimal? And I would say, absolutely not. We've given up in various places, and in our work, we identify where they are. But the reason why, in some sense, is that, I mean, we still think this is pretty meaningful, even if the rates aren't optimal, because we're able to provide these quantifiable estimates of the minimizers of this non-convex, a priori NP-hard problem towards some very smooth limiting minimizer, okay? So it's this random non-convex variational problem, but we're able to actually provide quantifiable concrete rates of how it converges, all right? So now the question is, how do you interpret all of this? Okay, so one way you can interpret it is just, this gives us robustness guarantees. This gives us consistency estimates that one can quantify for very specifically quantified parameter regimes in terms of epsilon and n. But one message that I take away from this, and this is something that we haven't figured out exactly how to say yet, but I think that when one looks at the problem of partitioning in the continuum, this doesn't look like such a terrible problem a priori. This doesn't sound NP hard. You could imagine, for example, using a mean curvature flow or something to try to find those minimizers. And of course, there should be local minimizers, but one should be able to, using something like this, at least on appropriate types of sets, find good partitions in the continuum. And we've shown that the minimizers of this graph problem are very closely related to minimizers of the continuum problem in precisely quantifiable ways. So one could hope that using these two ideas together and the fact that the limiting variational problem is so well behaved, has so much regularity, one would hope that one could say that partitioning these random geometric graphs might not be so bad, that it might not be this worst case combinatorial problem, that there might be good ways of doing this. But up to this stage, this is completely unknown. This is very speculative. Just in conclusion, one of the big messages I want to say today is that I hope that you've got the impression that the intuition that we get from continuum variational problems and their analysis actually give us quite a bit of leverage in studying these Cheeger cut problems or these clustering problems. But perhaps a bigger theme that one could gather from this is that continuum analysis provides a lot of new tools and avenues for studying ML algorithms. And here I'd make a big list of semi-supervised, active, adversarial, Dirichlet. I list all of these different things, but really the takeaway that I hope to give is that there's a lot of kind of work and energy going towards this, and I think it provides a lot of new avenues for studying and understanding these ML problems using the ideas and tools from the continuum analysis. And kind of one of the specific takeaways from this, this talk here is that the notions of convexity and how to handle these probabilistic estimates are often clear in the continuum framework. And oftentimes we're able to better understand and analyze them first in the continuum framework and then use that to say something about the discrete problems. And with that, I think I'll go ahead and conclude. Thank you all so much for your attention.
Okay, thanks very much, Ryan. So if anyone has any questions, please feel free to put them in the chat or unmute yourselves and just say it out loud. Yeah, maybe to get started, I can ask sort of one question, and that's so you mentioned sort of near the start that this isoperimetric sort of problem has been it's perhaps the most studied problem in calculus of variations. So I guess my question is, what are the questions that people are asking, and which of these questions might also be relevant to this sort of discrete problem?
Okay, so there. Well, so a lot of the things that people try to say are things like how smooth how regular are the minimizers of different types of these variational problems built around the perimeter. And there was a lot of work that happened. I don't know if I can put an exact date on it, 70s, 80s, 90s, kind of that really explored how regular these things are. It turned out that once you had that they were very regular, then you could study things like stability of these variational problems in very concrete ways. And I would say that in the last 20 years, there's been a lot of work trying to take the intuition and tools from the regularity theory and using that to then infer something about the stability of these variational problems. In particular, in the type of work that we did, we kind of, in some sense, you could see it as kind of like a grandson of, kind of a descendant of this early work on regularity. There's all this work on regularity, which led to this work on stability, which then let us say something about these Cheeger type problems. So.
Okay, thanks. Yeah, if there are any other questions, please feel free to ask.
Can I ask something? So you mentioned that the n to the minus 1 over d is very likely not optimal. And of course, if the dimension is high, that is a very undesirable lower bound. And I'll ask again about the measure mu, I guess. If you've got something that is concentrated on a lower dimensional manifold, for example, would you get the 1 over dimension of the manifold?
Yes. So actually the result, so here I kind of stated everything just to make it more concrete in terms of omega subset of RD. But the way that we actually posed it in the paper was we thought about a compact manifold of dimension m that was embedded in RD, and all of the rates are stated in terms of the dimension of the manifold. So that is actually very helpful in the sense that if the data is concentrated on a lower dimensional manifold, you really just see the dimension of that manifold and not the dimension of the higher, the kind of space everything is living in. So, nice. In terms of the measure mu, so we kind of embedded everything there into the metrics. on these manifolds. And we didn't, and then you can use the, all that you need is the regularity of the isoperimetric, of the minimizers of the isoperimetric problem, which holds as long as your metric is sufficiently smooth. So I think we only needed something like C4 or C3 at the end of the day. And so as long as your density has comparable regularity, I think it all works. I'd have to double check how we posed it all, but I'm pretty sure that was the case.
Okay.
Okay, so I guess if there are no further questions, thank you again, Ryan. It was a really great talk. We do have a meeting next week. There is a, well, at least for people in the UK, I think it's likely to be a change of time as we switch time zones. But this will be to be confirmed later. Yeah, so I say thank you very much, everyone, for joining us, and see you next week.